Welcome back. These are the chapter 7.2 notes. This is page 2. So we're going to take a look at something a little different. In example 5, we've got variables on both sides. Now, if we go back a minute, example 4, when the variables were on the same side, we would combine them. We combined like variables and then went ahead and solved. Here, though, it's different, because I cannot add across the equal sign. This represents something different on each side. What we need to remember is that our variables just represent a number, and we can do operations the same way we do with numbers. So I want to get all the x's on the same side. And when I say that, I mean what I want to do is get rid of the x's on one of the sides. So I'm going to go ahead and subtract this 4x. It's smaller. I'm taking it away from 7x. That's going to leave me with a positive number of x's. That makes my life a little easier. But whatever I do on one side, I have to do on the other. 7x's minus 4x's, it's like we're counting kumquats. 7 kumquats minus 4 kumquats leaves me 3 kumquats. I still have this $4 out here. I haven't done anything with that. And now this is just a two-step equation, the same that we solved above. I'm going to subtract 4 from both sides. I get 3x equals 3. Divide both sides by 3, so it's the 3 in front of the x that we're canceling. X equals 3 over 3, which is 1. Do the same thing here on B. This would be a good time to pause and give it a shot and then come back and compare your answer. I'm going to start by subtracting the 2x. It is the smaller. Again, I just like keeping it positive if I can. 3x's minus 2x's leaves me 1x. Again, I don't have to write the 1 in front. I have this plus 1 equals negative 7. Keep in mind, I got rid of the 2x. This negative still stays attached to that 7. Now I'm going to subtract 1. Negative 7 minus 1 is negative 8, and I get x equals negative 8. Oh, not what I thought it was going to do. All right. Now, example 6, we're going to get more practice with what we just did. We are going to solve equations where there's more than one operation. So I've got 3x minus 7 equals 11, and there's a couple different ways we could think about it. We are going to do our inverse operations. We're going to go in the opposite order. Okay? And I like to think about getting rid of the dangly bits, the stuff that's not directly attached to the x. So I'm going to start by adding 7 to both sides. Because if I'm going to divide by 3, I'm going to have to divide everything. And I don't really want to divide the 7 and the 11 by 3. Okay, so I'm going to do this addition first. Addition or subtraction always happens first. Now when I have just 3 x's on this side, I can divide both sides by 3. And I get x equals 6. So B, go ahead and hit pause. You can give this one a try. And then come back and double check. So I'm going to start by subtracting 7. I get my x term by itself, 2x equals 14. Divide both sides by 2, and I get x equals 7. Please make sure to look back through these and be comfortable with the order these operations happen in. Example 7 is combining a couple of things. So if I go ahead and take a look, my left-hand side has an a term and a constant term. I can't do anything with those. But on my right-hand side, I've got this 3a plus a. So I can combine those. 4a minus 3, and over here I got 4a minus 3. And now I notice that something looks weird. Both sides are exactly the same. Okay, now, if I go to move all the a's to one side and move all the constants to the other, I get 0 equals 0. This statement is always true. So it means it does not really matter what I plug in for x. I am going to get the same thing on both sides. This means I have infinitely many solutions. If we end up with an equation that's always true or both sides look the same, infinitely many solutions. So let's see what happens here on B. Can't combine anything on the left side, but on the right side I can definitely combine my x's. 1x plus 2x gives me 3x. I have 3x minus 7 equals 3x minus 11. And this looks a little weird. But I am going to go ahead and add 11 to both sides. And then go ahead and subtract 3x from both sides. And now I get 4 equals 0. This is never true. There is nothing I can plug in for x that is going to make 4 equal 0. So this one has no solutions. There is nothing I can plug in that is going to make 4 equal 0. So let's take a look at a couple more here. C has a set of parentheses, so I have got to go ahead and distribute this before I can do anything. So 28 on this side, nothing's happened. I got 7x. Negative 3 times x is negative 3x or minus 3x. Remember the negative, the opposite, the minus, those are all interchangeable. I have negative 3 times negative 4. That gives me a plus 12 here. 28 equals 4x plus 12. I'm going to go ahead and subtract the 12 from both sides. I get 16 equals 4x, and when I divide both sides by 4, I get x equals 4. Keep in mind, it doesn't matter if the x is on the left side or the right side. This is an equation, and those sides are interchangeable. D, and I'm going to move the D here really quick. I'm going to eliminate that so I can show you what's going on. I can multiply both sides by 8 and divide by 5, or we can use the trick we used on the first page. I need to get the times 5 and the divided by 8 both gone. So I'm going to multiply by the reciprocal. So if this makes you a little uncomfortable because we don't like working with fractions a whole lot, 8 times 5 is 40. I got 40x up here. 5 times 8 is also 40. I set this up so my 40s cancel. That just gives me 1x. Over here I have 30 times 8 divided by 5. Because I don't have a calculator handy, I'm going to divide the 5 into the 30 part. We can think of writing 30 as 5 times 6 times 8, and then cancel the 5s if that makes you feel better. We get x equals, what is 6 times 8? 48. E. Again, let's see if we can get rid of that label. We don't want to add and subtract all these fractions. So we want to get rid of the fractions. I am looking for the least common denominator. Okay, and my least common denominator here is 12. Because I can make a denominator of 12 by multiplying 2 times 6, and a denominator of 4 I can make 12 by multiplying by 3, and that 3 I can make 12 by multiplying by 4. So I'm going to do this a little different, and I'm going to multiply everything by 12. And when I say everything, I mean everything on both sides. And I'm going to go ahead and write this out. This is 12 times 1z over 2. 12 times 1 over 4, 12 over 4. 12 over 12, and 12 over 3. This is helpful because what happens now is I can rewrite this with entirely whole numbers. 12 divided by 4 is 3. 12 divided by 12 is 1, and 12 divided by 3 is 4. I get 6z equals, let's see, 3 plus 1 is 4, plus 4 is 8. We divide both sides by 6, and I can reduce that into 4 over 3. 2 goes into both 8 and 6. My last one, F here, don't necessarily want to add and subtract with a whole bunch of decimals. So I'm going to get rid of the decimals the same way we got rid of the fractions. And because this is going to one place, the tens place, I'm going to multiply by a power of 10 or a factor, multiple of 10 with 1 0. I got 10 times 2.8, that's 28. Multiplying by 10 moves the decimal, makes our number 10 times bigger. 1.4 times 10 is 14. Sometimes we look at this and we want to divide by the smaller number. We got to remember that we need to divide by the number that's being multiplied by x. That's the one I'm trying to get rid of. I get x equal 1/2. If you plug that into the calculator and you got x equal 0.5, that is fine as well.